So in this class, we are going to focus on the first derivatives of any given function in order for us to determine the values of x. We do understand as we work with the first derivative from our differentiation or the differential calculus. The first derivative where it is used, it is for the gradient expression. It is actually representing an expression for the gradient, which we then use according to the value of x at that point to determine the gradient. So in actual sense, if I'm given a quadratic, let's say we've got a parabola there. When a line is drawn at any point as a tangent, it is representing the gradient at that point where it is drawn, because the gradient changes, the steepness of the slope is changing until we reach the maximum turning point, or it can be a minimum turning point, meaning to say we have an increase. The steepness of the slope is increased positive up to the turning point. Then we're going to have a decrease. We are talking about the first derivative gradient expression. So meaning to say, as we consider from f of x, the original function, what we simply need is to understand the increase or decrease of that function, where there is a turning point. Where there is a what? A turning point. So meaning to say, where there's a turning point, like for a quadratic, at the turning point, direct at the turning point, the first derivative is equal to 0. Whether it is a minimum turning point that you have, as long you're at the turning point, the first derivative there will be equal to 0. But in that case, it will be a decrease followed by what? An increase. So as long you consider the first, just consider how it is given in terms of the functions. Does it have a turning point? So going up an increase, it means that's a positive. The gradient is positive. Remember, all lines, when you draw a line like this, it has got what? A positive gradient. When you draw a line like this, it's going to have what? A negative gradient. So if you are going to draw a tangent like this, the gradient of that tangent will be negative. Look at the line, negative. So when you say going down, it's a negative in terms of what? In terms of the gradient. This is the same, going down, a negative, going up, a positive. As the line is going to be drawn, a tangent, it will give us a positive gradient wherever it will be drawn. So this is positive. But at the turning point, the first derivative is equal to what? Is equal to 0. So meaning to say, for a parabola, which has a turning point, for a parabola, we can have this also on a cubic function, a turning point, a turning point. Whenever you've got those two, a parabola or a cubic function, where as long there's a turning point, it can also be on the trigonometric. Maybe it's the graph of a sine, or it is the graph of a cos, as long there's a what? A turning point. So where that applies, the critical values or the critical value will be the x value at the turning point. What is the value of x, which is the at the turning point? This will be your comparison point where you compare the values to say, on this side, do I have an increase or do I have a decrease? So thus, our critical values in that case for a parabola, a cubic function, will be the what? The turning point. Will be at the turning point. Meaning to say, the x value at the turning point. What is the x value at the turning point? That is the major case. So let's say this is where we have got our x, and x is equal to a at the turning point. This side, we are having an increase. It is increasing, meaning that's positive. The first derivative is greater than what? Is greater than 0. Positive. Negative, this side, our first derivative is what? Is less than 0. This is the condition compared from x. So when you say this side, x is less than a, as we are talking about these values, x will be less than a. The other side, x will be greater than what? X will be greater than a, which is at what? At the turning point. So you make your comparison with the turning point. The same thing, if it is like this, the turning point is a decrease. It means our first derivative is what? Is less than 0, negative. Here it is what? Positive, greater than 0, compared with the turning point. So at the turning point, let's say our x is equal to a, the left side, it means these values, they are less than a. The other side, they are bigger than what? They are bigger than a, which is the x value at the turning point. A parabola is the best description because it has a turning point. So you compare from there. What about a straight line? For a straight line, if we are given a linear function, which is a straight line, the steepness of the slope represents the gradient, remember? So meaning to say, when we have a straight line, by just looking into the line, we can tell that the gradient is positive. When it is going up, an increase like this, it is going up, they're down, negative, a decrease. So meaning to say, wherever it is going up, an increase, the first derivative is what? Greater than 0. Here, the first derivative is what? Less than 0. This is the condition. The gradient is negative. The gradient is positive. This is what I'm trying to say. This is the same thing that you just need to apply. And on a linear function, the gradient is constant throughout. So meaning to say, once you say there is no a point which we can say it's a critical point in that case. The critical values, because throughout the line is what? Positive. Throughout the line, the gradient is negative. So the critical values will be from other graphs unless it is a condition. Maybe it is passing the x-axis where you compare from the x value to say according to the other graph when it is a product or something. But on just a normal function, this one, it does not have critical values. You just take as it is, meaning the x values will be like all x values, as long as it's a real number. So its critical values will be determined from the other graphs now that you'll be having. So as for this one, we just consider other graphs to say how the graph is drawn. Mostly when it is crossing to the x-axis, you must compare to the x value there, since you have to determine what the values of x. But as of the critical values, it is not limited at all. All right. Then a hyperbola on the other side, the other ones, guys, a log, exponential is just direct. You just consider, look at the increase or it's a decrease. All right. So I'm not going to waste much time. Let's just consider a hyperbola. A hyperbola always, it's important because of what? Asymptotes. They are symptotes. So once we've got these asymptotes, we can have this one, which is a decrease, or this one, which is also a decrease. So according to the asymptotes, we can measure what is the x at the asymptotes, the value of x there. It is the one that is determining. Going this side, our values, they are less than what? They are less than a at the asymptote. Going the other side, our values, they are greater than a. But in the case that we can consider, remember the first derivative, if it is considered this way, a decrease, whatever that you're going to have here, it's a decrease. So meaning to say, the first derivative will be what? Less than zero, as it is what? As it is a decrease. This one is also a decrease. So meaning to say also here the first derivative is what? Less than zero. We've got a decrease. But if it is this one in the second and this one in the fourth, remember this one is increasing as the x values are going up, the y values are going up. So that's an increase, meaning to say whenever there is an increase, the first derivative is what? Greater than zero. The first derivative is what? Greater than zero. It's all about, is there an increase or what? Increase going up, positive, going down, negative. So this is what you're gonna have. So guys, I'm not gonna waste your time. For a log and exponential, you just have to compare, even if it is a log and exponential. Let's say we have got y is equal to whatever e to the exponent of x, a to the exponent of x, and exponential. What limits now are the asymptotes. In our case, maybe the x-axis is the asymptote. We are limited to the x-axis. The y-axis is there, having the values. But now we must consider to say, is the graph increasing or what? So as you can see, it's an increasing function. So meaning to say, throughout where we are going to try to determine our gradient, it is what? Positive. So meaning to say the first derivative is going to be greater than zero. It's just a comparison now that you just make. Is it going up or is it going down? But these are the major ones that you must consider: a hyperbola, straight line, quadratic, or a cubic function where there are turning points. Whenever there are turning points, you must consider the critical values from the what? From the turning points. The critical values will be at the turning points. So for a hyperbola now, what will be the critical values? The critical values, as we are comparing our x, is compared to the what? To the asymptote. So meaning to say your critical values will be the x value, at the what? At the asymptotes. The x value of the asymptotes. X value of the asymptotes. You see, grammar and mathematics does not go hand in hand. You see, now I want to write grammar here, all right? X value of the asymptotes. So that's it. So meaning to say, those will be your critical values. All right. The linear function, it's not limited. It's not limited. It's not limited. It is a condition now that you have to compare with what you're given. All right. So this is how you might be given conditions where the first derivative is there. So when it is greater than zero, simply means it is what? It is positive. It's positive. Less than zero is what? It's negative. There is an increase. All right. It is going up, or it is what? Or it is going down. So with this information, I just want us to consider some few examples, all right? And also typical exam, like how questions can be given in terms of an exam type. All right. But this is it, guys. Do not worry about much. It's just what is important is to note the critical values. All right. The critical values in terms of the functions that you are given. All right. Let's consider an example where we have got something like this. Just gonna put an example here. Let's say we've got our f of x, which is a quadratic. All right, something like this. All right, this is a quadratic. That's our f of x, and it has the x-intercept at -4, and this one at 1. And the turning point, if we add these two, then divide by 2, it's going to give us -1,5 or -3/2. That's the x value at the turning point. All right. This is our turning point, x value. Okay, this is our function. With the given graph, the questions can be, all right, let us say we are given the first one to determine the values of x for which the first derivative is less than or equal to 0. All right, it can be less than 0, can be less than or equal to 0. All right, remember we are talking about the first derivative. So as long we have got first derivative, you look into the increase or decrease of the given graph. So since we have a quadratic, which is a parabola, we said its condition will be limited to the what? To the turning points. The turning point will be your critical value. So meaning to say you are going to have your vertical line to the turning point at what? -1,5. This is our critical value. At x is equal to what? -1,5. There is this side of the graph and also this side of the graph from what? -1,5. So you ask yourself now, what is happening from the first side of the graph? As we are going the x values, what is happening with the y values? It's a decrease, a negative, meaning to say our first derivative is also a negative. There's a decrease. The other side from the turning point as we are going up, it's a positive. It is going up. It is positive increase. The first derivative is greater than 0. At the turning point, the first derivative, that is where it is equal to 0 at the turning point. So since they said less than or equal to 0, you must also consider that value of x at the turning point. It must be also part of your solution. So which one do we want? Where it is what? Negative. We need this region, negative. When it is going down, the function is decreasing. For these values of x, when the function is decreasing, that's the first derivative is negative. So compared with -1,5, we are saying, therefore, our x is less than what? This side, this is to the left side of -1,5. So it's less than what? -1,5. But remember, there is an equal to, which is when it is equal to 0, direct at what? -1,5. So you must also put the equal to. If there was no equal to, you're not going to put it there. All right. So meaning to say the other region satisfies another inequality, which could have been given as the first derivative with respect to x is greater than 0 this time. When the first derivative is greater than 0, it means when there is what? An increase, positive, an increase, where it is going up. From minus 1,5 at the turning point, the graph is going up. So therefore, x must be greater than what? Minus 1,5. Those are the values. If they wasn't equal to, you're going to put it also on your solution. So this is how you answer these questions. You work with the turning point where there's a turning point. From the turning point, is it going up or is it going down? Going up, positive, that's an increase. Going down, that's the first derivative is what? Is a negative in that case. All right, so like I said, it's just a matter of working with more questions. Let's consider this type. We dealt with a similar diagram before, but in this case, we want to attempt the question where we are to determine the values of x for which the first derivative is greater than 0. We are considering f. So in our case, do not worry about the hyperbola. Our question is not on the hyperbola, guys. Our question is on f. So the focus is on what? The focus is on f, of which f is what? A quadratic. So what is important on f is the turning point, and the turning point was at this point where x is minus 2. All right, this is our x-axis where x is negative 2 at the turning point. So we judge or we compare with the turning point. That is our critical value, remember? So at minus 2, we are comparing to minus 2 as we are going like this up to where x is minus 2. What is happening? That's an increase. It's an increase, positive. From minus 2 at the turning point like this, what is happening? The graph is going down. That's a negative. So we need where it is a positive greater than 0. So where it is a positive, that is the values from the turning point going this side, minus 2, minus 3, minus 4, and so on. So these values, they are what? Less than minus 2. So therefore, x is less than minus 2. Just like that, where the first derivative is greater than 0. We are comparing, we are working with what? With f. If it was on G, let's say they are asking the question there on what? On G. Since G is part of a hyperbola, it has got asymptote. We work with asymptote, and the asymptote was at the turning point at minus 2. So let's say they're asking the first derivative when it is less than, all right, where this is greater than, let's just say less than 0, guys, all right? Less than 0 like that. We just want to maintain the same thing like this one. All right, this was greater than, all right, let's do it like that, no problem. So when it is less than 0, we're talking about G this time. So you're just looking into G. So for G, since it's a part of a hyperbola, its critical values will be with the what? The asymptote now. The x value at the asymptote. And that's the x value at the asymptote, it was minus 2. So you compare from there. From minus 2, you check, all right, the graph, what is happening? It's a decrease, right? Remember that shape from the explanation that we had before. All right, let's just hope I kept, let me just remove this one so that I can show you those notes. All right, so if you check here for a hyperbola here, the first and the third, these two, they have a decrease. So this is the same condition of our question here. That's a decrease. So it is limited to the critical value of what? The asymptote, where x is minus 2. So from there, x is supposed to be greater than what? Minus 2. As we are going to the right side, x is greater than minus 2. X cannot be equal to minus 2 because it's what? An asymptote. We are talking about G. This was for f. For f, we are talking about this is your f. You compare it as it is f on its own, the f of x. Going up to the turning point, it's an increase. Going down, that's a decrease. So where it is greater than 0, where it is positive, those are the values of x on this side of what? Of -2. So they are less than -2. So answer the question. Answer the question. All right. On this other question that we are given here, we were given we're given this function, which is f of x. It was actually f of x, which is a hyperbola. That's our f. So the question, all right, did I put that question? All right, let me just write it down. The question here was to determine the values of x for which the first derivative is greater than 0. That was our question, of which the first derivative is what? Greater than 0. So I want you to understand this. Let us go back to our hyperbola, the same hyperbola that we had before. All right, I want us to get rid of this one. I want us to get to these notes, all right? Remember this hyperbola, what I was explaining. What is important, the critical values, which is what? The x value of the asymptotes. So in our case, this is the part of our asymptotes, all right? -1. So our graph is limited with or to -1, where x cannot be equal to -1. But from that -1, as we go to the left or as we go to the right, there's something that is happening on our graph. All right. So the question is, what is happening on the left side? We can see that the graph here is making an increase in our x values. All right. It's making an increase as y is going up. That's an increase. And this one is also an what? It's also an increase. Both are going under an increase. Exactly what we need here. The first derivative, where it is what? Greater than 0. That's an increase being what? Positive. So meaning to say, I talk about this interval as part of our solutions represented by x values that are what? Less than -1. So therefore, x is less than -1, or here limited from -1 to the other side. So x is greater than what? -1. So in actual sense, as for this one, we can just say x cannot be equal to -1, but x is what? X is a real number, any, because it is what we have this side and what we have on the other side. So it becomes your solution, or you can just have it this way. X cannot be equal to -1. This is how you answer derivative. There's no need for you to differentiate that to say, all right, I'm gonna differentiate. And if I differentiate, because whatever that you're gonna have, guys, even at any point that you'll be having, if a tangent was to be drawn, it is still under an increase. At any point, if the tangent was to be what? Was to be drawn, it was still gonna be an increase for those values of x that you'll be having. So it will be increased throughout. All right, a tangent of this nature is an positive gradient. So you just need to work out as many questions as you can where you do not understand. Let's communicate so that we can work on those questions separately. You just need to refer to the part that you do not understand. That is the major case. All right. So we are going to look into other questions as we have the basics now of this, the first derivative concept, how to apply it on its own. Use it now to answer questions where it can be f of x times its first derivative. It can be f of x times the derivative of gx. You must consider them as two different functions, f of x on its own, its derivative on its own. So its derivative, this is the part that we're working on, to say you just consider being the steepness of the graph. Is the graph the steepness, is it going up or is it going down? So that is the only thing that you can use to answer these questions graphically. Remember, you are not to differentiate, you are not to find these derivatives, because some of these according to your syllabus, you are limited to differentiate something like this. It will be very complicated in your syllabus because of the other methods which are not yet introduced in your syllabus. So you do not need to actually differentiate. No, unless it is a question which is not to be answered graphically, you want to have it by calculation. But if it is graphically, this information can help you to answer any question wherever it is to be done graphically. All right, so that is it, guys. Till we meet again.